Violent storms involve a lot of energy. Where does all of that energy come from? You are probably familiar with the blue ice packs that are used in ice chests to keep food cold. What makes them so good at keeping food in ice chests cold? It turns out that the same basic phenomenon that keeps the ice chest cool also provides the energy of storms. As we shall see in this lesson, both processes involve the energy associated with a phase change of matter. Remember that matter typically occurs in three phases: solid, liquid, and gas. We can illustrate this point with water, which can exist as solid water ice, liquid water, and gaseous water vapor. As we learned in an earlier lesson, the temperature of a substance, such as liquid water, is related to the average kinetic energy of its molecules. The individual molecules in liquid water have a wide variety of kinetic energies. Sometimes, a molecule near the surface of the water has enough energy to break free from the liquid. This phenomenon is known as evaporation. The evaporation rate of liquids is greater at higher temperatures because at higher energies, more molecules have sufficient energy to escape. Because the most energetic molecules are lost during evaporation, the liquid left behind is cooled. For this reason, evaporation is a cooling process. Solids can also evaporate directly to the gas phase. This is known as sublimation. Sometimes gas molecules near the surface of a liquid are attracted to the liquid and become liquid. This process, in which the gas changes into liquid, is known as condensation. It is the reverse process to evaporation. What do you think happens to the temperature of the liquid during the condensation process? Correct. The temperature increases. Condensation is a warming process because, as the energetic gas molecules become liquid, they transfer energy to the liquid. If a liquid is heated to a certain temperature, evaporation can take place throughout the liquid. Bubbles of gas form in the liquid and float to the surface. This phenomenon is known as boiling. The temperature at which a liquid boils depends upon the combined pressure due to the surrounding liquid and the atmosphere. At normal atmospheric pressure, water boils at 100 degrees Celsius. A sealed pressure cooker causes the pressure of the vapor above the water to increase. How do you think this increased pressure affects the boiling temperature of the water in the pressure cooker? Correct. The boiling temperature of the water increases. Because of the increased pressure, the water molecules must be more energetic to form bubbles. As a result, boiling occurs at a higher temperature. Another type of phase change takes place when a solid melts and becomes liquid. In order for a solid to melt, it must be heated until the molecules are energetic enough to break the strong bonds of the solid. Freezing is the reverse process of melting. In the freezing process, a liquid changes to a solid. All phase changes involve a large amount of heat energy. Let's conduct an experiment to take a look at the energy associated with phase changes in water. First, we take a chunk of ice at a temperature of about -3 degrees Celsius and place it in a beaker at room temperature. The ice begins to heat up, but doesn't melt yet. Eventually, the ice begins to melt at 0 degrees Celsius. What happens to the temperature of the ice-water mixture as heat is added and the ice continues to melt? Correct. The temperature remains constant at about 0 degrees Celsius. Why does the temperature of the ice-water mixture remain constant? Because the input heat energy is being used to produce the phase change, rather than to increase the temperature. The heat involved in a phase change is called latent heat. For a solid-liquid phase change, it is known as the latent heat of fusion. After the ice completely melts, what do you think happens to the temperature of the resulting liquid water? Correct. The temperature begins to increase. The temperature of the liquid water continues to increase until it reaches about 100 degrees Celsius. When the temperature of the liquid water reaches its boiling point at 100 degrees Celsius, another phase change occurs, from liquid water to water vapor. The temperature stops rising and remains around 100 degrees Celsius during the phase transition. The latent heat of a liquid-gas phase change is known as a latent heat of vaporization. The heat energy involved in the phase change of a substance is given by the mass of the substance times the latent heat. The SI units for latent heat are joules per kilogram. Another commonly used unit is kilocalories per kilogram. Now we understand why latent heat was the answer to our earlier questions. The blue ice absorbs considerable heat energy in the ice chest, while maintaining a constant cold temperature due to its latent heat of fusion. When water vapor in a hurricane condenses as rain, considerable energy is released due to the latent heat of vaporization. This energy then drives the intense winds of the storm. Now let's put to use what we have learned. We'll start with an insulated cup containing 100 grams of water at 20 degrees Celsius. If we add 10 grams of liquid water at 0 degrees Celsius to the cup, the final temperature of the mixture is 18.2 degrees Celsius. Now, suppose that, instead of adding ice water, we add 10.0 grams of ice at 0 degrees Celsius to the cup. The final temperature of this mixture is 10.9 degrees Celsius. In this case, the extra heat energy needed to melt the ice caused the final temperature of the mixture to be much lower. Now we know why adding ice is a good way to cool a drink.